calculus of industrial food processing, soft fruit is a liability. It is structurally incompetent, unpredictable, messy. Consider the papaya. Flesh with the consistency of room temperature butter. A skin tougher than leather. A core loaded with chemically volatile seeds. Yet, in supermarkets from Seattle to Savannah, millions of cans of tropical fruit cocktail boast papaya cubes of geometric perfection. Razor-sharp edges, uniform density, zero bruising. How do you coerce a fruit that wants to liquefy into a perfect cube at a rate of nearly 9,000 pounds every hour? Welcome to the paradox of high-speed fruit processing. To achieve this, gentleness is not an option. We must subject it to controlled violence. We will boil it until its skin detonates. We will spin it to G-forces rivaling a fighter jet. We will fire compressed air ballistics at it. This is no kitchen. It is a fortress of stainless steel and precision hydraulics. Here, 150,000 pounds of raw, irregular biology are tamed into standardized, shelf-stable precision. The process begins with an avalanche. The logistics of a modern papaya facility are dictated by decay. The moment a papaya is severed from the stalk in the humid plantations of the Americas or Southeast Asia, its internal clock starts ticking. Enzymes immediately attack cell walls. The flesh softens. The supply chain becomes a race against biology. Trucks hit the receiving bay in a synchronized, relentless loop. Each rig hauls 20,000 pounds of raw fruit, 48 hours off the tree. But the connection to the farm ends here. As the tailgate drops, the fruit enters a sterile ecosystem, governed purely by machine logic. The first adversary is mass. Papayas dump into a receiving hopper, a steel gullet sized to swallow the payload of two full-sized pickup trucks. A metering conveyor at the base regulates the chaos. Too much fruit jams the cutters downstream. Too little starves the line of efficiency. Volumetric sensors throttle the belt speed, maintaining a steady, relentless curtain of product. Before processing, the fruit endures hydropressure decontamination. They ride an inclined elevator into a wash basin that is less a bath and more a tactical assault. High-velocity water jets blast away field debris, dried sap, and hitchhiking insects. Note the water's agitation. This is a turbulent flow system. Air bubbles injected from below create a boiling cauldron effect, rotating the floating fruit to ensure every square millimeter of skin meets the chlorinated solution. Technicians monitor parts per million levels in real time. If sanitation dips, the line halts. From the tank, the fruit ascends to the sizing deck where a diverging roller system sorts by diameter. As the gap widens, smaller fruits drop out, leaving the behemoths to carry on. Why size them? Because the machines ahead operate with tolerances measured in thousandths of an inch. A papaya too large jams the intake. One too small gets obliterated. Uniformity is the prerequisite for automation. The fruit is clean, sized, and primed, but it remains encased in a tough, armored epidermis. In the kitchen, a human hand would wield a knife, but manual peeling is economic suicide. A blade is flat, a papaya is curved. Trying to square that circle shears off valuable orange flesh. Manual peeling forfeits nearly 20% of the yield. In a plant running almost 9,000 pounds an hour, that is nearly 2,000 pounds of wasted profit every 60 minutes. The solution isn't a sharper blade. It is thermodynamics. The papayas are fed into a monolithic vessel that resembles a reactor core more than a peeler. Once the 1,100-pound batch weight locks in, the hatch seals hermetically. The machine injects superheated steam. Internal pressure spikes to nearly 200 psi, 15 atmospheres, in a blink. Inside this pressurized hellscape, the papayas tumble. Heat penetrates the skin, but only by a fraction of an inch. The objective is not to cook the fruit, but to turn the moisture trapped just beneath the skin into a thermal bomb. This lasts exactly 15 seconds. Then, The machine triggers the flash. A release valve snaps open, dumping pressure from 200 psi to 0 instantly. Basic physics seizes control. The superheated water under the skin flashes into steam, expanding 1,600 times in volume. It has nowhere to go but out. The skin doesn't peel. It detonates. The chamber door swings open, and the fruit tumbles out shaggy, their skins hanging like wet rags. To strip this debris, they pass through a dry brusher where counter-rotating rubber pintles, soft, mechanical fingers, wipe away the exploded epidermis. The result is an engineering miracle. The fruit is nude, smooth, with virtually 100% of the flesh intact. Yield loss plummets from 20% to less than 8%. But a new problem emerges. The fruit is slippery, wet, and delicate. And it hides a bitter secret at its core. A raw papaya is a biological vault. Its center cavity teems with hundreds of black seeds, each encased in a gelatinous sac and coated in benzyl isothiocyanate, a chemical compound with the flavor profile of crushed pepper and battery acid. One crushed seed releases this bitter agent, ruining the entire batch. If a seed breaches the final can, it is a critical failure. The factory must extract the heart without breaking the body. The naked papayas are marshaled into single-file lanes. Slippery and erratic, they are corralled by a V-cup conveyor that cradles each fruit, orienting it vertically. A pneumatic guillotine slices the fruit longitudinally. The cut must be dead center. Lasers scan the geometry milliseconds before the steel drops to adjust alignment. The halves fall open, exposing the seed cavity and move onto the cleaning deck, cup side up. Here, industrial microsurgery begins. A phalanx of robotic probes descends from overhead. These aren't scrapers, scraping tears the soft flesh. These are high-flow vacuum nozzles, synchronized to the belt's velocity. As they descend, they breach the cavity of the moving fruit. The rhythm is mechanical and relentless. The vacuum exerts a precise suction force, violent enough to rip the seed mesh free, yet gentle enough to leave the fruit undisturbed. It is a precarious balance of airflow and pressure. Too much suction, and you cannibalize edible product. Too little, and the seeds cling on. The tolerance is less than 1/10 of an inch. The probe hovers just above the surface, using air velocity to lift the seeds out. The waste, a slurry of biological shrapnel, is sucked away for reclamation. The papaya halves exit as pristine orange vessels, clean, seedless, but they are still large, irregular hemispheres. To transform them into the cubes found in a fruit cocktail, they must survive the most violent machine on the floor. We return to the central paradox. Papaya flesh is soft. Push a papaya half against a stationary grid of knives, and it won't slice. It compresses, it buckles, it purees. To achieve a clean cut, the fruit must be rigid. Freezing destroys the texture, so we use physics to fake rigidity. We use a G-force. The fruit enters the impeller housing, a stainless steel centrifuge spinning at 1,200 revolutions per minute. Dropping into this maelstrom, the halves are instantly pinned against the drum's inner wall by centrifugal force. At this speed, the fruit experiences forces many times that of gravity. The soft flesh compresses against the steel until it acts like a solid block of wood. It is no longer fruit. It is a projectile traveling at 60 miles per hour inside a circle. Pinned to the wall, it slides across a slicing gate, a razor edge set at a precise depth. Because the fruit is moving fast and pressed hard, the blade shaves off a perfect slab. It is the principle of a carpenter's plane applied to biology. The process accelerates. The slab hits the crosscut spindle, a rotating cylinder of vertical knives chopping it into strips. Finally, the circular knife spindle obliterates the strips into cubes. Slice, strip, cube, All 3 cuts occur in less than the blink of an eye. The engineering tolerances are razor thin. If the impeller spins too slowly, the fruit slides and jams. Too fast, and the G-force crushes the cellular structure, causing the fruit to bleed juice. Engineers have dialed in a sweet spot of velocity where the fruit is solid enough to machine, but the cells remain intact. The result is a cascading waterfall of tens of thousands of orange cubes. To the naked eye, they look perfect. But in this facility, the naked eye is obsolete. Dicing is a violent affair. Occasionally, a fragment of skin survives the steam, or an overripe piece turns to mush. In a stream of cubes moving at 6 feet per second, human eyes cannot track every defect. This job demands the most advanced optics on the floor. Digital sorting in freefall. The Papaya cubes launch off a shaker table, forming a wide, flat sheet of falling fruit. Mid-air, they traverse an inspection zone bombarded by cameras and lasers. Cameras scan for color, green skin, dark bruises, but the lasers analyze internal structure, measuring light scattering as it penetrates the flesh. A firm, healthy cube scatters light in a specific signature. Mush does not. The processor builds a real-time digital map of every falling cube. It spots a defect, a speck of green. It calculates the cube's trajectory, velocity, and its exact position 5 milliseconds in the future. Then, the invisible sniper takes the shot. A bank of air nozzles spans the drop zone. The processor fires a precise burst of compressed air, a bullet of wind. The airjet snipes the specific defective cube, knocking it out of the stream and into a reject chute, while the good product falls undisturbed. The system can fire hundreds of times per second. To the observer, it looks like sorcery. Bad fruit simply vanishes from reality. The system culls 99% of foreign material and structural defects, leaving a stream of pure, high-grade product ready for the can. The sorted cubes race to the filling station. Exposure to oxygen is the enemy. Oxidation turns the vibrant orange-brown. Empty cans arrive on a magnetic conveyor, twisting like a metallic snake, inverted and blasted with ionized air to strip dust before flipping upright. A rotary volumetric filler uses telescoping pockets to drop the precise measure of fruit into each can as they whirl around the carousel. But dry fruit is useless. It needs a suspension medium. A nozzle injects a hot solution of water, sugar, and citric acid. This syrup enhances flavor and acts as a thermal conductor for the sterilization to come. The machine leaves a precise headspace, a gap of about 3/16 of an inch at the top. Without this buffer, thermal expansion would rupture the can. Next, the seamer closes the vault. As the lid drops, a jet of steam blasts across the top, displacing air in the headspace. The seamer chuck spins the can, while rollers curl the lid under the lip and flatten the metal into an airtight double seam. When the trapped steam cools and condenses, it creates a vacuum, sucking the lid tight and starving internal bacteria of oxygen. The speed is blinding. 600 cans per minute, 10 cans every second. But the fruit inside is not yet safe. It is raw. It carries natural microbes. If left alone, it acts as a fermentation bomb. It requires the kill step. Sterilizing a can of papaya is a thermodynamic puzzle. A static steam oven would burn the fruit touching the metal walls, while the center, the cold spot, remains lukewarm. Lukewarm is dangerous. It allows Clostridium botulinum to survive, to ensure every molecule hits the sterilization target of 250 degrees Fahrenheit. The factory deploys a rotary retort. Robotic arms stack cans into steel cages, which slide into a massive cylindrical pressure vessel. This isn't just an oven. It is a washing machine for steel. Once locked and injected with steam, the entire internal cage rotates. This rotation is the secret weapon. That headspace bubble we left in the can travels through the syrup as the can flips end over end, acting like a mixing spoon. It forces hot syrup from the shell to the core. This forced convection drives heat to the cold spot rapidly. Engineers track the F0 value, the calculated lethality of heat against bacteria. They need a value of 3.0 to guarantee commercial sterility. Rotation hits this target in half the time of a static cooker, killing the bugs while preserving the crunch. Once the target is reached, the retort floods with cold water, halting the cooking process instantly. The cans emerge cool, sterile, and ready to survive the apocalypse on a pantry shelf. The journey concludes at the palletizer, where robotic arms stack cases with hypnotic precision. But what of the waste? The explosive skins, the bitter seeds, the rejected mush. In a facility processing over 200,000 pounds of fruit a day, the waste is massive. It does not go to a landfill. Beneath the floor, a network of flumes flushes this organic sludge to a separate facility, the biodigester. Here, in massive anaerobic tanks, bacteria feast on the papaya debris. As they eat, they release methane gas. This gas is captured, compressed, and piped back into the factory's boiler room. There is a poetic symmetry at work. The methane from the papaya skins burns to create the steam that powers the peelers to strip the skins off the next batch. The fruit fuels its own destruction. From a chaotic, rotting crop in a muddy field to a sterile, geometric, shelf-stable dessert. This is the triumph of industrial engineering. We have taken nature's softest, most fragile creation, and through steam, lasers, and G-force, we have built a fortress around it. That is how the modern papaya is made.